start with case 2? Think about your equations that we wrote. Why did we really need to start with case 2? Guys, look at your equations. Why do we need to start with case 2? Because you had to subtract 2, right? So we can't really do 1, we can't really do 0. Like physically, each of those equations we had to subtract 2, okay? So one painted face, we were looking at 0, 6, 24, 54, 96, 150, and, oh, we didn't go past that, 216, right? No. Yeah, 216, okay? And so when I look at this, right, a lot of us were freaking out a little bit, like, Mr. Kenny, I don't know. Now, some of us did recognize right away that if we look at this equation, what type of function does one painted face have to be based on this function, or that equation? Oh no. Say it louder. Quadratic. Why do we know it's quadratic, guys? N minus 2 squared. Nice, we got a quadratic. Okay, so quadratic, now we've studied this before. What type of rate of change should that quadratic have?
Linear additive.
Should have a linear additive rate of change. I'm going to break this down. I need us all paying attention to this a little bit. Not a little bit, a whole lot of it. This is a foundational piece that I never was taught, and it blew my mind when I learned it, because I guarantee you, if you study calculus later, this is going to make calculus a ton easier for you, okay? You don't have to study calculus, but 1, it's beautiful. 2, this is foundational, really, really, really help. Okay, so, notice that's definitely not constant, is it? What's happening, though? Adding by 12, right? Do not forget, because I keep hearing people talk about, oh, it's constant linear additive. No, 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 no. Constant means what? Stays the same, right? There's only one place up here that I have a constant rate of change. Where is it? The what? Oh no. I'm sorry, on the dependent side, right? Here, what am I going to call this? Guys, that's the same, isn't it? The blue? So what are we going to call that? Constant, what? Constant additive. Remember, I don't call it the rate of change, because only here is my rate of change, but that's constant additive. And Davis, what type of function had a constant additive rate of change? Oh, Davis, we got to know this one, huh? A linear, right? A linear function had a constant additive rate of change. So what are we going to call this rate of change right here? Guys, the rate of change. Guys, this is constant additive. Thank you, it's linear additive.
Wait, what'd you say?
Notice, constant additive to linear additive rate of change, which is what made this what type of function? Quadratic function, okay. Woo-wee. Does that sound familiar? We've heard this, we've explored this. Yes, Drake? No? Maybe? I mean, like, does this sound familiar? Okay, so we've explored it some. We comfortable with this idea, Jaden? Yes? Shadidra? You good with this? You sure? Your face tells me a different story. Are you good with this idea that this quadratic function has a linear additive rate of change? And how we're identifying that? You sure? Okay, just making sure. Mary? Yes? Kelly? Elizabeth? Hope? Yes? Landon? Been out for a few days. We good? Okay. So, looks like we're doing okay. Malia? Fantastic. Alright. Now, we got to move past that, though. We've got a new function on the horizon, or not really horizon. We're there. Alright, so 0 painted faces. Case 2 had 0 painted faces. Case 3 had 1, or cubes with 0 painted faces. Was this 24? No, 8. I know how to do math. 5 was 27, 6, 64, 7 was 125, 8 was 216? Is that right? Okay. So, when we looked at this, we talked about, or we wrote the equation n minus 2 cubed, so we knew what kind, this was what kind of function? Cubic. By the way, what degree is a cubic function? It's a third degree, right? It literally is cubed, okay? So, we need to now understand our rate of change. All of us were doing this, as far as I could tell. And so, be careful. I will say this, I'm not going to ask you to do this a lot, but if you get off by one set of numbers, everything gets thrown off after that, okay? So, to go from 1 to 7, 6. Man, I don't have a single thing that's constant yet, do I? But what's happening to that dark blue, that navy blue? It's adding by 6. So Shadidra, what am I going to call this purple region right here? That's what? The thing I just circled. Huh? Say again. It is the rate, well, be careful. Remember, only here is my rate of change, but this is some type of rate. What type of rate is this? Let me ask you this. Is it changing or is it staying the same?
Well, the
The same, right? So we're going to call that. Kyron, help her out.
Constant additive.
So if it stays the same, what do we call it, Kyron?
Constant additive.
Well, just one of the words. Constant. We're going to talk about the other one in a second. Shadidra, if it stays the same, what do we call it? Constant, right? Like, it's staying the same. It's constant, okay? And what are we doing with that? What did Kyron say? We are adding, so we call it a constant additive. Okay? Now, Mary, help me out. Remind me, what type of function had a constant additive rate of change?
Linear?
Linear? What do y'all think? Linear?
Come on.
Sound right? Okay, linear. Okay, cool. So what, Mary, am I going to call this blue piece right here?
Constant additive rate of change. No.
Remember, the purple was
Oh,
constant
sorry.
additive.
No. Yeah. Constant multi. No, constant linear. What do we call it? Linear.
Just linear.
Linear additive rate of change.
Remember, the word constant means it stays the same.
Oh, sorry. Yeah.
So, because this was constant additive, this navy blue is
Linear.
linear. And what are we doing with that linear set of numbers? Adding. So it's linear. Okay. Now, Bella, help me out here. Remind me, what type of function had a linear additive rate of change? Quadratic. So, almost instantly earlier, Elizabeth, I heard you say that you thought this was going to be what type of rate of change? This is a rate of change, and we are adding, and its rate of change is linear. So this rate of change is quadratic additive rate of change. So what makes a cubic a cubic? Quadratic additive rate of change. Okay, I'm going to have you take some notes to your future forgetful self in a second, but before that, I need to emphasize something. I want us to notice, okay, when it was y equals, let's say, x squared, that is quadratic, right? The rate of change was what? The rate of change was linear additive, which would look something like this. That's linear, isn't it? Okay? Okay guys, pause for a second. I need y'all to notice this extension because this is why I took all this time. If it's y equals x cubed, what type of rate of change is it? Quadratic additive. So something like y equals x squared. So let's say we extend that. And I jump to y equals x to the fourth. Any guesses what type of rate of change this might have? Cubic additive? So something like y equals x cubed? Just a guess? I will go ahead and confirm that guess. what's the relationship between a polynomial and its type of rate of change? Well, how did you know it was going to be cubic additive? If I extend this and I go to y equals x to the fifth, what type of rate of change is it going to have? To the fourth power. So what's happening to a function to get its rate of change? What's that minus 1? The power, right? Aren't we taking the power and subtracting 1 from it? That's actually one of the most foundational ideas for when you study calculus and you start talking about this thing of derivatives. Hopefully you remember that word. If you don't, it's going to be okay. But if you take calculus and you start hearing that word derivative, I want you to recognize that that rate of change, the power is just decreasing by 1. So when we talk about polynomial functions, the rate of change for a polynomial is, first off, notice every polynomial has what mathematical operation for the rate of change? What mathematical operation? I was saying, aren't we adding? Didn't we say additive this whole time? Yes? So the rate of change for a polynomial is additive, and by a polynomial, that's not how you spell nominal, that is, what's the relationship between the degrees? What are we doing to the degree?
Subtraction.
So it is that polynomial that is the degree minus 1. That is a fundamental truth that holds for every polynomial function that you will ever explore. The rate of change for a polynomial is additive, and by a polynomial that is the degree minus 1. By the way, typically when we say degree, we use the variable or the letter n, if you want to put that on there. I don't think it was going to be on here. If I were you, I would put this on the back side of the very first Frere model that I gave you, unless I can find a different one that's better. I might have made one. That's not the one. Hey, it's okay. We learn from our mistakes. It is totally okay to make mistakes. Alright, so on the back side of that first Frere model, I want us to make that note to ourselves. One, very important, a cubic function has a quadratic additive rate of change. And then that extension into the idea that the rate of change for a polynomial is additive, and by a polynomial that is the degree minus 1. What's up, Taylor? Gotcha. Landon, did you get these Frere models before you left? My God, you got to ask for these things.
Oh, that is,
Anybody else not have these Frere models? Did anybody else need the Frere models? Right there, aren't they? You just need that one.
Mr. King, which Vermont is there right now?
I would put it on the front of the one that just says constructing polynomial functions. The very first one, page 1.
I gave y'all a lot of good pointers.
Hey guys, I need us to quickly write these notes because we are, which part of it was my mismanagement of time at times, but we are about a day and a half behind where I need to be. So I need us to quickly take these notes so that we can get to the next part of this lesson. So we need a test early next week. Why is it not printed? There we go. Sorry, I have it printing, but my printer is literally taking forever. I don't know what's going on. It's been telling me it's receiving data forever. That's only the good old tech issue of just turning something off and back on for solution. Alright. You having fun there, Peyton? Ready to start? Alright. Oh, Leah, that's it right there.
It's A.
Leah making me print something. Is that a 5x5x5?
Yes, it's a 6 by 6.
Oh my goodness, that's extra.
And then
Well
one
done.
has 7.
Wait,
It does. This one has 7.
now you were actually here for this one. I know, because we started it.
Yeah, I got this.
Yeah.
I'll thank you. I didn't write it.
Alright. So, really quickly, who can I coerce / get to do Hero Friday tomorrow? We need somebody. I want to hear about you. Yeah, that's what I like to hear.
You gotta do a brief.
Oh my God, Taj going tomorrow? I got.
Yeah, Taj is going tomorrow in 3rd block.
Can I come listen to that?
Sure.
I want to
Okay.
I got Miss Peach. She's here.
Alright. So, we don't have time to go over the demonstrated understanding today. We'll do that tomorrow. I just want to do a quick reminder. This is what the demonstrated understanding yesterday was about. This is also in all the YouTube videos that I've posted from class to help explain ideas. Guys, if you miss a day, or 3 or 4, please make sure you take advantage of those videos to grow and to learn. So that foundation I'm going to skip over, but remember, the old proficiency scale was all about sketching polynomials. when given the graphs of the factors. I'm going to have you do a reflection tomorrow when I pass your other ones back, your other proficiency scales back. But what we are focused on today is identifying domain, range, and intercepts of a polynomial, determining standard form of a polynomial by multiplying the factors, and then rate of change. So I will point out what we just talked about was the rate of change for those functions. That is a foundation piece, and then those foundations should sound super familiar. There's various ways we can identify the multiplicity of zeros and roots. We can do it algebraically or graphically. That's what we'll get into heavily tomorrow. And then we're going to be looking at the degree in both factored and standard form tomorrow. So that's a big part of tomorrow. The rest of that is today. So, for the sake of time, we're going to talk about this together. Page 156, please get that book, or that page out from the book. Okay? No, you can look at it right there, for right now. Most of the instructions I'll give, you can just look at that sheet. Okay, so what we're looking at, what we're quickly talking about here is this. We're going to use this equation. It was based on the getting started that goes with the textbook. But Lewis, Ahmed, and Heidi each use graphing technology to analyze the volume function from the beginning of this and to sketch the graph. They disagree about the shape of the graph. Lewis said the graph increases then decreases. It is a parabola. Ahmed said the graph lacks a line of symmetry, so it can't be a parabola. So just looking at those graphs there, who do you think is right, Lewis or Ahmed?
Lewis.
Lewis? Why are you thinking Lewis, Landon?
You don't have to have a long symmetry.
What doesn't have to have a line of symmetry? The graph? Okay. Anybody want to add on to or push back on that? Any thoughts? Okay, I want y'all to talk about it in small groups. I want y'all to talk about that idea because I need to have some ideas. I don't want to just tell you if you're right or wrong. I want you to think. Talk together for just 60 seconds. Who is right so far, Lewis or Ahmed, about the line of symmetry idea and whether it is a parabola? Just comparing Lewis and Ahmed right now. Yeah, I'm just asking you to compare Lewis and Ahmed, not necessarily getting into height. Right? I'm just asking who's right and who's wrong. Because Lewis is saying the graph increases and decreases, so it's a parabola. Ahmed just says the graph doesn't have a line of symmetry, so it can't be.
Aren't they the same?
I know that they have different reasons. Yeah, they have different reasons.
So what are y'all thinking? Lewis is right? Why is Lewis right? Okay. Miles, you look like you're not sure about that.
It's linear additive, and the end wouldn't go up. Linear additive, it wouldn't raise and start changing. What do y'all think?
Okay, so let's bring that back, let's talk about it. So, anybody want to add on to or push back on Landon's belief about not needing a line of symmetry? Hope, you want to push back? Did y'all talk about it some?
I think Ahmed is right.
You think Ahmed's right? So, you're thinking it's not a parabola because it doesn't have a line of symmetry. Miles, go ahead. It looks like it's going to curve back up, okay? So I also want, Miles, I want you to share what you were saying in your group about that line of symmetry.
It's still there.
Oh, like, it still has like some line of symmetry, even though you don't know. Like,
So-
you know the line of symmetry, but it's still-
I'd say when we talked about parabolas in the past, what are the 5 features of a parabola that we always looked at?
X, Y,
X-intercepts, Y-intercepts, concavity, line of symmetry, and what did every parabola have, guys? A line of symmetry. A parabola, by definition, that quadratic, is symmetrical. So if it doesn't have a line of symmetry, could it be a parabola? No. Look at what Heidi said. I noticed the graph, someone was saying this earlier, I think Hope you were saying, right? It looks like it's going to curve back up, right? Heidi says, hey, it curves back up, so it can't be a parabola. What type of function is this? How do we know it's cubic? It has 3 roots. I can see that, right? We want to notice, and I hope we're starting to recognize this shape. When we start to see this shape, that should make us think about a cubic. We're going to explore it more heavily later. But that's a cubic. It's got how many roots? 3. There we go. Now, here's what I need us to do with the 15 minutes we have left. I need everybody to have a calculator in hand, and we're going to type in this equation. Pause. Make sure I finish the instructions first. We're going to type in this equation, and what are we going to change our window in the calculator to? Look, yeah, negative 10 to 15 needs to be my x-min, my x-max, my y-min, and my y-max. So when you get your thing graphed, it's going to be hard to see things unless you change the window to that. So make sure you change your window settings to those values. Sound good?
Yeah.
All right, one person per group. Grab calculators. Start working on this. Let's figure this out. Grab calculators for the whole group. One person per group. Grab calculators for the whole group. Sorry for that confusion.
This is frozen.
So guys, please notice it's page 157. Typing in and graphing the function that is on the board. It's fun. Let's graph our function though. I didn't do it intentionally. Type that equation. By the way, you're going to have to put a multiplication symbol between the x and the parentheses when you type that equation in. I don't know why the calculator doesn't recognize it, but it doesn't. That's right. You ready? Well, you haven't typed this equation into the calculator yet. No, you ain't. You're trying to look through your papers.
I just got my paper.
Did you put the?
Okay, this is what it should look like. Now, Miles, ask that question again. Looks like a bunch of lines. Did you change your window yet? No. My guy. What's the button that does all cool crap on this calculator? Menu. Well, use your eyeballs. Where am I going to go to change the window? Window/zoom. Ah! Where then now?
Window settings.
Oh, window settings. What did I say for the X-Men? I think it was negative 10 to 15, right? So the X-max is 15. What's my Y-min? Y-max. Does it still look like a bunch of lines, Miles?
Yeah, it doesn't stop. It keeps going.
Thank you. Thank you. So let's bring it back. Let's talk about it. So, all right, I'm going to give a word of caution about the way that I hear someone talking about it. Bella did a great thing that I want to encourage. She found her notes from the other day when I gave the hints and the suggestions to help you with Mathia. But Miles, talk to me about this. Why did you say the domain was negative infinity to infinity?
The domain is left to right. Keep going.
Pause for a second. When you say left to right, what do you really mean by that? Say that again. I need y'all to hear me clearly on this. You cannot just talk about domain as left to right. Why? What did I just talk about with y'all?
Because you can do it with not having a graph.
Guys, you can have domain, a function has a domain without a graph. The domain was the set of all what? What did you say? There's another word I thought I said, if not, let me add this. Say it again. Inputs. Guys, you can have inputs without any kind of graph. Right? It's important to recognize that domain is a set of all inputs or x values, which is why I look left to right, Miles. But it's all about those inputs, those x values. So when I look left, does it ever quit going left? No. Does it ever quit going right? So what's the minimum? And so here's the other thing I want us to recognize, and I need us to be careful about this. When we use interval notation, do you know which number or value always goes first? Which number always goes first in interval notation? Say it again. It's the minimum. So like you can say left versus right, but really when we say left, we're talking about the minimum x values. When we talk about right, we're talking about the maximum x values. When we use interval notation, it's a minimum to a maximum. It does not matter what you are doing with interval notation. That's what this is called. It is a minimum to a maximum. Always focus on that, which is why, and like you said it, you got to answer right, Miles, but originally you said top to bottom, didn't you? And you had to fix it. That's fine, right? We learned from it. But where's my minimum? Is it at the top or is it at the bottom? It's at the bottom, right? So we talk about range. So domain was the set of all inputs or x values. My range is the set of all outputs or y values. Okay? And so if I'm looking at a minimum, does it ever quit going down? No. So the minimum is negative infinity. And does it ever quit going up? So the maximum is a positive infinity. Guys, the Matthew assignment I gave you was not just to give you an assignment. If you are not seeing this domain and range right away, you can go redo it and practice it. You need to practice it. We've got to know domain and range, okay? Now, what I want to do really quickly is, they're asking right here about the maximum, and we're going to talk about the minimum. Now, here's my graph, all right? Jaden, can you come up here and circle where you think the maximum on that graph might be? Now, mind you, do you have to have a graph to find a maximum?
No.
No, but a graph is where it's easiest to see. Where do you think? Okay. So, technically, it keeps going, right? That's what you said, Jaden? So is there actually a maximum if it keeps going for forever? No. So in this one, and I'm glad you actually asked that. One, be careful, not a parabola. What could I call this region though? It's concave down. This is one cubic function, but you can say it's the concave down piece. But there's not an absolute maximum here. And so there's a difference between absolute and relative max. If I were to say relative max, a maximum that is relatively more than everywhere else, what do you think it would be, Jaden? Because you started to point here, didn't you? Why is that a relative maximum? Because what?
Well, you can actually see it.
You can actually see a number, but also I want you to think about this. If you were thinking about this like a roller coaster, what's going on here? It's going up. What's a mathematical term for that? Increasing, right? All the way through here, what's it doing? It is increasing. What's it doing after it increases? It starts to decrease. And so it's the top of the roller coaster. So if it stops increasing and it starts to decrease, it's a, what do we call that? I just said this. Relative maximum. Okay? That's what I was asking for, is a maximum value, right? So what do we call this? A relative maximum. Anyone want to take a guess what I'm going to call this down here, where it stops decreasing? It's going to be a relative minimum, okay? And so it then starts to increase. So a relative min. Now, I hope you didn't put your calculator away because I'm going to show one last thing and I want you to take a picture of this and put this in your notes in a second. What's the button that lets me do all cool crap? Menu. Menu. Okay, so I'm going to go to menu. And I want to analyze this graph. Does anyone see anything that might be helpful to analyze this graph based on what we just talked about? Yeah, but like inside the analyzed graph, anyone see anything useful? Oh, there's a minimum and a maximum. That's it. I want us to find that maximum. Notice it says lower bound. So we just need to go to the left and hit enter. And when it asks for an upper bound, I go to the right and hit enter. And that calculator can tell me what the maximum is. Okay? So we're going to do more practice of this tomorrow, but I do need you to make sure you note this. Relative maximum. How do we get a relative max? It stops, it stops what? Increasing and starts to decrease. Notice that's going to happen between my roots and my zeros. When's it going to be a relative minimum? When it stops decreasing and starts to increase. Guys, please make sure you take a picture of that before you leave today. Put this in your notes.
For real.
Yes. So, let me find it. We're going to talk about this more tomorrow. But I need you to pay attention to this. So right here. So like you took all this time to distribute and get your standard form.
I was trying to get, so I got stuck.
Figure out the concavity.
Okay, and then I was trying to put it in vertex mode so I could find the vertex.
I know. But what I'm trying to tell you is you're making this harder than you have to do. What we're doing is we have this function g of x and we're dilating it by f of x. G of x has a 0 right here. And so notice how I'm multiplying this. That's an output and that's an output. So that's my output, that's a 0. It doesn't matter that this is negative 2 point something. What's 0 times negative 2 point something? So my new function is going to have a 0 right there where that factor has a 0. My new function is going to have a 0 right here where this factor has a 0. Okay? Then when I look to the left over here, are these values right here positive or negative? Okay? Now remember, and I just want to make sure this is clear, not because of the x, but because of the y. When we say values, we're talking about the outputs, right? Are these positive or negative? And what happens when I take a negative and I multiply it by a negative? You see how all these values are positive? Right here. These y values, are they positive or negative? And these are, these right here, in between. Because notice, I'm looking between the zeros. Look again. Are these y values, those are negative, they're below the x-axis. And what's a positive times a negative? And so, we go into the negatives, but it's got to turn around. And I'm not terribly concerned about the vertex. It just got to turn around and get back up to my 0. And then when I look to the right, these are all positive, these are all positive. And what's positive times a positive? So, it's positive here. Because what you're doing is not going to work. So you started to do it here, this is going to be easier, but my point is it doesn't work when we start to get to these cubics. Now, what you need to be careful about is how many lines do I have? You only did positive times negative, but isn't this also down here? So really it's times negative. And so positive. And so like I know you were trying to just kind of figure it out like after this one section, but if you look here, positive, positive, times a negative is what? So you see how that goes into the negatives? It's got to come back up to here. Now, from this 0, positive, positive, negative. Right, notice how it's negative? And so make a note about that double root, because I can see that, but you didn't explain that. But notice, yeah, it's a double root, so it's negative, and then it bounces back down to being negative. And so like, because this one section was off, all the rest of it's off. You see all the work you had to go through, and all you had to do is negatives times negatives. I'm just trying to make your life easy. the whole idea is using my factors to see what a sketch of this function will look like. Go for it.
I'm sure we'll go over it tomorrow.
We will.
But
So
I
remember how we're, and I was curious to see what we did with it. Remember how, see how we're multiplying these y values? You see how this is a 0 for g of x? Wherever g of x has a 0, h of x will have a 0. So there's a 0 right here.
turn my phone down.
See how there's a 0 right here? So wherever f of x has a 0, h of x will have a 0, because I'm just multiplying these y values. But guess what's negative 3 times 3? That's not a 0. So it's wherever these functions have zeros that my dilated function is a 0. That's why we did this, right? Wherever this factor had a 0, my dilated. Does that make sense now? We'll talk more about it tomorrow. Okay. Yeah. Yes, ma'am.
I should be fine to go tomorrow.
In a way.
Yeah. And if you need me to, I'll email him. Who is it? He'll probably be fine with me, yeah. Just tell him to email me if he is upset.
How do I have a 41 in geometry? You have a 41 in geometry?
Just not turn it into a sign. You didn't do the learning day assignment. That's how you have a 41.
Wait, no, because
Advisory, I don't know where the heck everybody is, but y'all need to do the next piece of the schmoop. Reading today. Reading was tied for my second highest section of the ACT.